can start right now. Hi everyone. I wish you guys had a great weekend and get some rest from first week of online education. Just before I start, I wanna remind you that I sent you an email um, over the weekend, just reminding you if you guys have any difficulty in terms of IT, accessing the material, uh, invitation to the lecture. I don't want those to be in our way. So let's get together. Let's try to fix it and make sure that you guys don't have any IT problem as much as we can. The second thing, I think we discussed the last class about the breakout group. I think this is something we will need because we cannot really see each other or maybe discuss in this big group. So we have to, not a choice, not a choice. We have to break out our 33 students into smaller group. Only couple of groups responded to me. Even one of them is not complete. So it looks like you guys are maybe you don't know each other. Maybe there's no chance for you to coordinate that. So at the end of day today, if I don't hear from you, although I said it's Sunday, midnight is your deadline, but if I don't hear from you until the end of today, I'm going to myself go ahead and then split you guys into smaller groups, and it will be not really super science. I'll just go with the name list, and I'll go five or six in the same group. Okay.
How
Hey,
did
sir. Oh, sorry. Go ahead.
thank you. How did you want us to like I myself have a breakout group, but how did you want us to notify you? I might have missed if you told us. I'm sorry.
No, there was who's that? Your name is, please.
Dominic.
Okay, Dominic. So I think I sent a separate email, and that's why I said uh, you need to check your email probably twice a day, even in the weekend. I sent separate email, and I think this was even before the weekend, so the weekday. And I asked you guys to only one person from the group. When you internally coordinate that, I want only one person to send me like the name of the group, five or six students. Um, so anyway, so if you have a group, that's fine. Just email to me, and I will just set about the group. Probably this afternoon.
Okay.
Okay. Thank you, sir. That being said, let's start on our way today. Today we have I think we left this document, which we talked about the structural design. We discussed the process, and I think now we also, if you guys remember, at the very end of our last class, we mentioned about two names that you will remember for the entire course, and you will also learn this in other class with Corwin. The first name is ultimate limit state, which is a state of the structure uh, where the structure or when the structure is about to collapse or fail. It is something that, as a designer, we have to look at and then prevent and stop. Okay. Number two, serviceability limit state, which we refer to as SLS. So those are another state of the structure, which is not really when the structure is about to fail. However, this is happening every day, which we call it performance. So those performance criteria, like deflection, vibration, and permanent deformation, we need to look at those and make sure that our structure will not fail, and on the same time, it's going to have a satisfactory performance in every day. Now, I think where we stopped last class is we looked at this like this equation. So I'm going to draw a box around this equation. It is not really an equation where you directly substitute in, but it's kind of a conceptual equation, which as soon as I start, you will see it will completely make sense to you guys. Now, let me introduce for you two terminologies. Number one, R. You see in this equation, capital R on the left side, and the R is very simple. R is the resistance of the member. And I can say also the capacity of the member. In plain English, how much this member can take until it fails. Okay? Now, on the other side, there is something called S. And S is simply the internal forces that is coming from the load affecting the structure. Okay? So, I mean, we can simply, if I write here for you guys, if I write equation here, so I'm going to write the R one more time. So this is the capacity of the member. I'm going to write here another time. I'm going to say here S is the internal forces due to the acting loads. So let me ask you one question, which you will see it's supposed to be a very simple question. For my structure to be safe and does not collapse under the acting loads, okay, what it should be the relationship between the capacity of the member and the internal forces from the load? Would you say it has to be larger, or it has to be equal, or it has to be smaller? I need you guys to turn on your mic if you can, and then just, you know, all you have to say, the resistance should be more the internal forces, or the resistance should be equal the internal forces from the loads, or finally the resistance should be less than the internal forces from the load.
The resistance should be more than the internal forces.
The resistance should be less than the SI.
The resistance should be more.
Yeah, the resistance
Guys,
should be
it's
more
not a
than
fight, okay? Okay, cool down, please. Okay, no
yeah,
fight here, no fight here, please.
okay,
Okay.
okay. Yeah, the resistance should be more than SI.
Thank you so much. This is thank you. We're in agreement right now. So guys, look at this. If my, let's say, let me give you an example by number. Let me give you an example by number. If I have a beam and this beam, its capacity, it can take maximum. Look at the name, capacity. It can take maximum of 200 kilo Newton meter a moment. If I apply 180, then still fine, because I'm below the capacity of the member. If I apply 190, great, still great. The beam will survive and can take and withstand the load. If even the beam, even if we apply exactly 200, this should be still okay. However, as soon as we exceed, our forces exceed the capacity of the member, then here we go, the beam will die, will collapse, will fail. So hopefully, guys, you agree that if we want to have safe design, then the capacity of the member, or we call it resistance, this should be more than the internal forces caused by the loads. Okay, so you can see we have here, we can put here another relationship in between, and I can say larger than. So the relationship right now is set. Let me convince you and develop the discussion. When we say larger, do you think this statement is going to be subjective? When I say subjective, it means how many times should be larger? Should my capacity, like the beam capacity, should be twice as much as the loads, or 3 times, or 100 times? Let me ask you, I'm going to give you some numbers, so you guys, you know, maybe think loudly. How about if I put, you know, I get a beam, and this beam, the capacity of this beam, let's say, is 4,000 kilo Newton dash meter. So this is how the beam, you know, can take, maximum it can take. And then the loads, my loads affecting this beam, it causes only this much in the beam, 200, or let's make it simple, let's say 400 kilo Newton meter. Okay. Now, I'm asking you a very simple question. What do you think about this design? First of all, is it safe?
No.
Unmute your mic and tell me.
Yes, it is.
Can
No,
take 4,000?
Yes, it is.
It's very safe.
Safe, yeah.
I like that whoever said the word very, okay, very safe. Yes, of course, it is very safe because it can take all the way to 4,000, while we are only subjecting this beam to only 400. Okay,
Yes,
you can
sir.
see I like the
Sorry.
word. I like the word very safe. I like it very much because it's
Sir?
true. It is. can you please like, try to regulate like, how much you interfere? Like,
Oh,
just comment please when I ask you to unmute. Otherwise, it will be chaos. Okay. So if I ask you to to unmute your mic and then speak, yes, of course. But as soon as you do that, please go back and mute yourself, please. Thank you. Okay. So as I said, if the beam has very high capacity as compared to the internal forces from the loads, then we're very safe. But the question is, the word very safe, does it give you a good feeling or a bad feeling?
Very good feeling.
Okay. Anybody else to have an input?
Very good one.
I kind of disagree with that.
What?
I disagree with when you say very safe or good feeling when it's 400 to 4,000.
Okay, thank you so much. Mute your mic. I like what you said. Me too. I kind of disagree, because if we go this way, if my loads causes 400 and I design my beam to have a capacity of 4,000, in engineering and in design, they call this one overkill. It's over design. We have made our beam significantly larger than it should be. And by the way, you think this is good? Yeah, okay, fine. But are you that rich? When you build the house, would you be a bridge girder in a house? Doesn't because simply look at the money, look at the cost of this beam. When we oversize our beam, it means we're using more material than what we should. It means we're paying more money than what we should. Otherwise, I guess we go to the, I know that Egyptians are great. They built great structure, but look at the columns they built in their temples. The columns are oversized, so big, maybe for a different reason, maybe for architecture reason, but structurally, it did not need this big columns, okay? So let's agree that the relationship larger, so R is larger than S. It is very subjective, and it will lead to uneconomical design. So what is the other option? The other option is, this is the other option. I'm going to get rid of this. And you guys know so far that if I say less, it means no, that's wrong, because simply your member is going to fail. However, let's agree from now on that this is our best. We would like our resistance to be equal the internal forces. However, in our design process, we will do our best that the resistance to be lower than the load. This is something will never happen. So yes, we will do a little bit of margin. We will make sure that our resistance will be a little bit more than the S, but not as like the example. So this is too much. For example, I can design my beam in a way, for example, this is the case, okay? This is the case where the resistance or the capacity is going to be 405, while the loads will cause in this beam only 400. We're very much close to the internal forces from the load, but not significantly big, okay? So now let's develop this further, okay? Guys, let me ask you a few questions. What is the guarantee of the resistance? When I say I'm going to design this beam so that the beam can resist bending moment of 405, okay? Let's agree. What is the probability? And again, the word I'm saying is completely true, probability, okay? What is the probability that this is going to happen? Remember, guys, we're using materials. In this class, we're using two different materials. One of them is concrete, and the other one is reinforcing rebar. Those material, guys, maybe from your first year, I'm asking you, when we make concrete, do you think the concrete, if I make concrete and if I produce this much, and I've done the best effort to make the best design, but I'm asking you, when I make my concrete, what is the probability that all my samples, all my concrete will be like, for example, 30 MPa? Guys, you have been in our classes, you know what can go sideways or go wrong in concrete manufacturing. adding a little bit of water extra. What happens if it rains while you're pouring concrete? How about mixing? How about all those factors that you learned last year? When you think about it, you will see, no, if I cannot really trust, look at this word, I cannot really trust 100%. If you trust 100%, then the equation you see on your screen will be valid. But if we agree, all of us, that we cannot trust 100% the material, then we should do something about it. You agree? I want you guys turn on your mic. Probably I need to hear a few of you saying, yes, we need to do something about the variability of the material.
Yes, we need to do something
we do.
about it.
Oh, okay, perfect. Thank you so much. Okay, so how we do that? Look at the equation now. The equation will start to grow. So the equation you see on the right is a little bit different from the one on the left. The one on the left, you see before the R, there is a number or a factor that has been added, which in this equation, I use Greek letter, which I refer as phi. So the phi is number that has to be multiplied by the R. And why do we multiply the resistance by the R? Very simple answer, to account for any variability in the properties of the material that we're using. Now, I'm not gonna focus now for the other side. So let's focus so much for the phi, which is I call it. It has a name. It's called the resistance factor, as you can see in my document. And this one should reflect the uncertainty of the prediction of the member resistance, because we have change in dimensions and change in material and workmanship. So there are so many factors that can simply affect the resistance of our member. Yes, on the paper, we can say my concrete is 30, and we can do all the mathematics and all the analysis, but who exactly guarantees that we're going to get on site our 30 MPa? So this phi is simply something that we have to, not a choice, we have to consider to make ourselves safe. Now, I have a question for you, and this one is for Mark. This one is for Mark, okay? So guys, this is for 1% of your next assignment, okay? So I'm gonna say the question, and again, I'm not gonna make it random. You have to raise your hand, and then I'm gonna let you guys speak out, okay? So here is my question, and please, as soon as you know the answer, raise your hand. I will look back at MS Teams and see who raised by order. Now, when you think about this resistance factor, this number, it should be more than 1, or it should be less than 1, and why? So the question is, the resistance factor phi should be more than 1 or should be less than 1, and why? Let's go to MS Teams and see. Okay, great. Let's see. Okay, let's go with Jelly is on the top. I don't know if this is the same order that it was happening, but I have no other way to know what's the order. Okay, and again, guys, don't be so concerned. Again, there are so plenty of marks, so you will get 100%. I'll assure you will get some. So let's start with Jelly. What do you think? Is it going to be more than 1, less than 1, and why?
It has to be less than 1. Otherwise, if it's 1, then there is no point of factoring of putting that value at all, because otherwise it's gonna be the equal or the same with the on the left side of the SI.
Sweet. So let's go to the other part of the question. So why do you think should be less than 1?
It has to be less than 1 to make sure that the resistance is has the assurance that it is less more than, or not less than, the other side of the equation of the SI.
Thank you. The mark is awarded, but you know what? I want to award somebody else. So I'm going to get Diego, please. Diego. So could you please, if you can, if you agree on what you said on the first part, less than 1, so please do the second part, which is, can you reformulate why the phi or resistance factor should be less than 1?
Yeah, I agree with her that the factor should be less than 1 to account for any internal defects or whatever possible defects that the piece can have. So you are decreasing the resistance value to compare with the actual internal resistance.
Thank you so much, guys. Please put your hands down. Again, probably next question, I will exclude some to get everyone, to get some marks for everyone. Sunny, your hands are up. Do you have question? Looks not. So guys, let's look at this, please. Let's look at this, please. So you're right. The resistance factor, it's a reduction. It's a reduction because when we think about the resistance, there are two situations. We could be optimistic or we can be pessimistic. When it comes to the resistance, I would say we have to agree. We have to be a little bit pessimistic. We will say, okay, you know what? Maybe we are not getting the 30, but probably it's safer to you assume it's going to be only 20 because that's a safer for us. Okay, so the phi is a resistance factor. Before we move to the other side, let me please look at my screen here. So guys, since we have two different materials, remember, in our class, it's not our material. With Corwin, it's only one material, okay? With me, there are two materials to design your beam or your column. There is concrete and there is reinforcing bars. And that's why those numbers, they are different. And hopefully, I'm not going to make this question, but hopefully you guys appreciate that we must use two different materials. We cannot really make it the resistance factor for concrete same as rebar. And the reason is very simple. Concrete is kind of unhomogeneous material, is not really homogeneous, consists of gravel, sand, water, cement. There are so many things that can go sideways. You guys remember that from last year. However, rebar or steel is more homogeneous material. Whenever we have a homogeneous material and the mechanical properties of this material is very consistent, in this case, we can use a bigger number in terms of resistance factor, and you can see phi or phi sub s, which is for reinforcing bar, it is going to be 85%. And for concrete is going to be 65%. I have, guys, few notes here. So you guys please take some notes. Number one, please don't be confused because with Corwin, the number for steel is not going to be the same. In steel, I'm saying structural steel because those are different. Those are reinforcing bars. So for structural steel, you will see it is 0.9, so 90%. That's one thing. The other thing, those number, especially for concrete, those are not fixed. And I'm not saying they are going to change like in next code or something like that. However, I can share you with something with you. Back in 2005, the phi sub c was only 0.6. And what does mean after 15 years between 2005 and 2020? Actually, this has been changed in the code of 2010. So what happened is we kind of make a better concrete. We have more quality control. We have more quality assurance of our concrete production. And when we control the production of our concrete, we kind of control of those factors of how much water we add exactly, how much cement, probably we have better manufacturing process. And that's where we can simply adjust this number. It went from 0.6 to 0.65. This means we trust our process move. Okay. So anyway, before also I leave this part, here what's going to happen, and see that you will see this in every class in my course until the end. Look at this, please. I'm going to type in something. Okay, so in the last year you heard this name. Okay, did you ever hear this name? F sub y.
Yeah.
Do you guys know what does it refer to? F sub y. Did you learn it in any strength of material?
Yielded strength, yield strength.
Okay, thank you. Another mark for you. Okay. So yes, it is yield strength. And this is where the rebar will start to yield if you apply tension on the rebar. Okay. Guess what? In my class, you will never, ever, ever see this by itself, okay? So you will always see this and this. So those guys here, this guy here with this guy before. So you will see always the F field or the F sub Y always multiplied by phi sub S, always, never by itself, because we will never with F deal with F field. However, we deal with a reduced F field. Same. Let me ask you one more time. Did you guys last year learn anything about FC dash?
Yes.
Yes.
Please, next, not Jaylee, next. Who said yes next?
I'm saying yes, but I can't exactly remember.
Oh, that's fine. You know, no big deal. You know what? Just because you said yes, I'll give you a mark. What's your name, sir? Your name, sir?
Dominic or Domenico, I guess.
Okay, sure. Okay, guys, look at this. Really, really, as I told you before, I don't get those marks from my salary. If it doesn't come from my salary at the end of the month, trust me, I'll think 100 times before I do that. Okay?
Sir, it's not FC prime, but F prime C.
I mean, because I mean, I don't have WinWord, so if I do it with WinWord, it's gonna be like what you said. Okay? It's just that because I have I'm typing on a you know, PDF. Okay, so forgive me for that. But
Okay.
F dash C. Okay. Now, guys, FC dash, and thank you for Domenico. I want you guys to say something, because the more you say, the more you get involved with, don't sleep, then you will get the best out of this course. So FC dash is the concrete compressive strength. Okay, this where the concrete, and I apply this one, concrete will simply collapse and fail. In my class here, you will never ever see FC dash by itself. However, it is always preceded with this phi c, multiplied by this phi c. Okay, so in my class, you will see it's a twins, which means phi sub s always multiplied by F field, and always the FC dash is multiplied by phi c. Now let's go back to this equation one more time. So we kind of covered the left side, which is a reduced resistance. So we are going to say always our reduced resistance has to be larger or equal than the internal forces caused by the load. Now, I know that so far we covered the word S, and again, S, what is S? S is simply the internal forces caused by one specific load. For example, live load or dead load, okay? Now, why, or you can see there is a newer term here. If I'm going to point out to this term, okay? So there is a term here called alpha. Guys, look at this, alpha. Now, let me explain for you, why do we need to include the alpha, or why do we need to change our loads? Because there is also the loads, there is no guarantee that our design load will be constant at the same value. Sometimes you get some variability in the load, or uncertainty, or there is a probability of loaded change, and that's where alpha plays. We need to change our loads, okay? Now, I think a few minutes ago, we all agreed that the resistance factor, it has to be less than 1. The resistance factor, it has to be less than 1, because we're trying to be pessimistic, and we're trying to deal with the reduced resistance. It's better, it's safer for us. Now, a question for a mark, and I'm gonna, show you your hands, please, if you know the answer. So when it comes to alpha, and alpha is a load factor. Alpha is a load factor, okay? So let me ask you, the alpha is going to be more than 1, or equal to 1, or less than 1? Okay, my question one more time. The factored load alpha in the equation you've seen a minute ago, is it going to be more than 1 or less than 1? I'm going to bust a little bit, Jelly. Thank you for your contribution. I like that so much. But, I won't get everybody else to be involved with as well. Thank you. So I'm going to go with Siham.
I'm thinking it's going to be more than 1.
Okay. And why do you think it's going to be more than 1?
Because we have to design for snowstorms, windstorms, hurricanes. like extreme scenarios?
Yeah, I think, you know, without even using those you know, factors, we will have to do that. But the question is, why do we need to exaggerate and you know, magnify our loads? Because this is going to be safer for us. And so what happened is, thank you so much, thank you guys. So I'm going to switch back. So you know, what happens is we add those alpha or load factors to magnify. Look at this, magnify. It means the load factor will be more than 1. Okay. Now, when you think about this magnification factor alpha, you know, in the last class we talked about that the loads, they are not really from the same type. Our loads, they are not from the same type, because we have something called dead load, live load, snow load, wind load, and so on and so forth. Now, because those loads, they have different nature, and that's why also every single load, it has its own load factor. So we are not going to multiply the dead load by the same factor that we're going to use with the live load, and so on and so forth. Now, who exactly define those load combination? Okay, I mean, sorry, I kind of jumped a little bit, but let me go back, guys. When a structure, when I say structure, it can be anything. It can be anything. It can be a warehouse. It can be anything. Okay, so in general, when we say we have a structure, and this structure will be affected by loads, my question for you is, if we agree that the loads are dead load, live load, snow load, wind load, and so on, you think those loads will act individually on the structure, or they will act together on the same time? So you think the dead load will act by itself in some time, and then the live load will act in some other time, and you know, the wind in some other time, or the snow in other time? What do you think? So the loads will act individually, or there is a possibility and probability that they will act together on the same time? Please answer.
Individually.
They would act together.
Together.
At the same time, or sometimes it depends on it sometimes individually, or sometimes it is all at the same time.
They will
But
act
the dead load and the snow load, when there's a snow load, the dead load will also act at the same time,
Okay,
and
thank
the
you so
live
much.
load.
Thank you, Jerry, so much. Okay, guys, look at this, please. Look at this, please. That's true. Sometimes, like, look at the dead load. Dead load, from the name, it doesn't go anywhere. It doesn't go anywhere. It's the self-weight of the structure, which means there is no a single case where you see no dead load. Doesn't happen, because simply dead load is the self-weight of the structure. It stays there and stays there forever. However, yes, sometimes we are in class, so there is some live load. But sometimes, like the pandemic, there is nobody in the class. Okay. In winter, we get snow, but in summer, we get something called rain. Okay. So the fact is, dead load is always exist, but sometimes affect the structure by itself, and sometimes the dead load will the dead load is there, and sometimes you will get some extra or another load to act together with the dead load. Okay. Now, guys, who exactly sets those combination? We agree that the loads, they act on the structure in kind of combination. It means together. Okay. So which book, what exactly sets and defines those load combination? The answer is here. Let's go and look at this table here. So guys, this table, I don't know why the quality, the resolution is not great, but this table, and I'm not gonna go really into details, otherwise it will take long time, because this is another like a deep discussion later on in my class. But for now, to kind of move on to another topic, what you see here is a table that comes from the National Building Code of 2019, or the Alberta Building Code of 2019, or the National Building Code of 2015. Okay. So I want you guys to look, and I'm going to go only maybe for the first one and second one. So the first one is called case number 1. And this case, it says we need to study how our structure would behave and what are the internal forces due to 1.4 the D, which means the dead load multiplied by 1 plus 40% extra. Okay, guys, if I ask you in this discussion in load case number 1, where is the alpha? Where is the alpha? Where is the load factor? Anybody to turn on the mic in a second, tell me what's the alpha? What is the load factor in load combination number 1? Okay, guys, here is the load combination number 1. Here we go. This one here is load combo number 1. How much is my alpha?
1.4.
Thank you so much. Okay, so you can see here, in this case, when we apply dead load by itself on the structure, we need to use a dead load multiplied by 1.4. It means 40% extra of the dead load. Now, if we go to the load combination number 2, and again, you will see things will get a little bit more complicated, because when you look at load case number 1, it's only dead load. There is nothing else whatsoever affecting our structure. However, if you want to read load combination number 2, it is a little bit more complicated. And the way we read this one is, please listen to this. 1.25D, and then you see or, you see the word or, which means this is going to create sub load case number 2, and I will probably write all of them for you today. So it's going to be 1.5D, and then forget about this one for now, and then add 1.5 the live load. Okay, so it means on the structure right now, dead load is affecting, which will always be the case, doesn't go anywhere, and then the live load is also acting on the structure as something called the principal load. Please learn this name. So this name is very important, principal load, principal load. So in this case, because dead load is always there, so a dead load is always there. However, in every load combination, there is something called the principal load, which is acting in full. Now, when you look at this load combination is not finished yet, we also have to see what is the effect of 1 or 100% of the snow or 40% of the wind. So guys, whether the snow or the wind, what do we call them in this load combination? Please read this name. It is called companion load. So the companion load, look at the name, it's companion. It's not the principal load. It's a load that is affecting the structure on the same time, however, is not acting in full. Okay. Now, I want to show you that this is load combination is not really a one combination. It will generate 4 different alternations. Let me show you. So let me write for you here the 4 of them, which they are sub of load combination number 2. So 1.25 the D, okay, plus 1.5 L plus 1S, and this will be load combination version number 1, and then another one, it's 1.25 the D, and then plus 1.5 L plus 0.4 W, and then 0.9 D plus 1.5 L plus 1 S, and then 0.9 D plus 1.5 L plus 0.4 W. I'm hoping that you guys know why this happened, because the word or. The word or, it means this or this. So we have to try all different combination. Okay? Again, we will go through this in details. Really, what I want you to take from this discussion is, number 1, loads, they act together on the structure. That's number 1. Number 2, where do we get our load combination that we need to try and see what is the worst? Is simply from the building code, whether Alberta building code or national building code, the latest one, which is 2015 for NBC, and then ABC it's 2019. Okay. Now, third is, what do we mean by the principal load? This is the load that is the primary load affecting the structure, and then companion load, it is affecting but not. Because look at this, please, watch this. What is the possibility that in one day you will see we have all the students coming to the class, so we have one full load, live load, sorry, and on the same day we have a snowstorm, and then the same day we have a tornado. Same day, so all of them, they are affecting the structure in full. One more time, what is the possibility of one day that all the students, all the live load will go to the school, and on that day we have a snowstorm, on the same day we have a tornado? I guess this doesn't happen, okay? Otherwise it's a day of judgment, okay? So it doesn't happen. So someday, yes, we get all the students, we get a little bit of snow, a little bit of wind, so we call them a companion load. And some other day we have a snowstorm, and if we have snowstorm, the snow will be the principal, and then not every student will come to the class, some of them, okay, and we get a little bit of wind and so on and so forth. And you can see, once we move from load combination number 2, and then we go to load combination number 3, let me ask you, question for you for a mark. Question for you for a mark. In load combination number 3, what is the principal load? Let me see. Okay, maybe not enough time, so I'll go back. In load combination number 3, what is the principal load and what is the companion load? Rudy.
It looked like there was wind.
No, your sound, the sound is not really great.
Wind?
In load combination number 3, wind is what?
Sorry, 3, sorry. That would be a companion. In 3, it's snow.
Exactly, you can see where I'm pointing right now. The snow is the principal load, and the companion load could be the live load or the wind load. Correct? Okay. Rudy got one mark. Okay. Now, again, I mean, if you don't get it, trust me, we will go through this, this table every time we do a design. So please don't be concerned. Okay. Now, a few things before we finish this presentation, and then probably we will have a break, which is a few things to remember for this course. Let me remind you, for the units we're going to use for the entire course, we're going to use metric international units, which means for forces, and when I say forces, I'm referring to the shear force or the axial force. We're going to use a kilonewton, and this is how we always say, look at this, we always say Kn. So we never say kilonewton, we say Kn, or we use mega newton, which is 1 million Newton, because mega is 1 million and kilo is 1,000. For uniform load, linear load, we use kilonewton per linear meter. For linear load, like the uniform load on beams, we use kilonewton per meter. For area load, for example, for slabs, we use the units kilonewton per meter square, because that's a load per unit area, which is called kPa or kilopascal. So those are equivalent. 1 kilonewton per meter square is simply 1 kPa, which is kilopascal. For stresses, we use Newton per millimeter square, Newton per millimeter square, which is force per unit area, which is simply this Newton per millimeter square is equal to MPa, which is megapascal. This is something you guys are probably perfect, right? Because you've done this last year in your concrete class, or maybe strength of material. And then guys, finally, the moment, or the bending moment, okay? The bending moment, the units will be force times lever arm, which means a distance, it means kilonewton meter. Those are the units we're going to use in our class this year. 3 numbers, very important, that you guys will need to remember. And again, I will make you professional. You will just, memorize them by heart. 3 numbers, very important in my course. The density, concrete density, which we refer as gamma C, gamma sub C. So this will be 23.6, and it's a force per volume, which means kilonewton per cubic meter. And you know, I know that this number is kind of very difficult to memorize, so I make your life easy. We always instead we use 24. So 24 is a very easy number to remember. Kilonewton per cubic meter. So every cubic meter of concrete will weigh 24 kilonewton. Okay. Next is the modulus of elasticity, or Young's modulus, what if you will. So modulus of elasticity is called E sub S, and this is for reinforcing rebar. So this is 200 gigapascal or 200,000 megapascal. And then finally, the rebar yield stress, which we call it F sub Y. This is going to be 400 MPa. Guys, now before the break, let's see questions.
I got one. Back to that chart that you were showing the principal loads and the comparison loads.
Yes.
Sorry, companion loads. How would this? Sorry, this might be a really stupid question. How would you?
No, sir. Please don't say that. No stupid questions. No. Go ahead and say.
So when would you decide which principal load to choose? When you're designing?
Fantastic question. You know what? This is a smart question. So you know what? Okay. So our friend, your name, sir, please. Your name?
Dominic.
So Dominic is asking, you know, I'm a designer. I'm designing a beam. Okay. So should I, for example, use 1.4D, or should I use, you can see the number 2 already yielded to 4. So you can think about 2 as 4 different load cases. And you can see 3 will do another 4, which means another 4. Okay. And 4 will give you another 4. And 5 is only, looks like it's only, oh no, there is no or, so which means 5 is 1. So 1 is one load combination. 5 is one load combination. However, number 2 and number 3 and number 4 will yield 2 different 4 combinations. Now, here is the answer. Let me ask you, and probably you yourself will answer this question. Okay? So you are designing a structure. Should you design the structure for one specific case, and if the other case happen, and unfortunately the other case gets you into a bad more than what you anticipated, what's going to happen to your structure? For example, let's say under 1.4D, that moment will have 100 kilonewton meter moment. However, under 1.5D plus 1.5 live load plus 1S, the internal forces is more than 100, let's say 150. Should I design my beam for 100, or should I design my beam for 150?
150.
So you already answered it, which means in a design process, we will have to make all those load combination. We have to analyze our structure under all those load combination, and then we take the worst case, which is the maximum, and then we simply design for the maximum. So in case any of those happen during the lifetime of the structure, your structure will still be safe.
But when you're just calculating anticipated loads and then making a decision off that.
You will have to estimate all the loads, like the dead load, live load, and snow and wind. If some by the way, so you know, maybe sometimes you think that's very complicated. Sometimes, some loads do not exist. And I will tell you, for example, what? If you are designing your main floor house, like, your main floor in your house, on the main floor, is there any snow?
No.
However, the roof, is there any snow?
Of course.
Okay. Is there any live load on the roof? There could be some, maybe somebody's trying to fix the antenna or do something. So we have to consider some live load. But here we go. Although it looks complicated, but bottom line is we have to try all possible load, not impossible load, possible load. So if this is a possible load, yes, we have to try it. It's a must. Otherwise, if you only focus for one load combination and ignore the other, and then in real life the other load combination happens, and unfortunately, this load combination that you have never even considered yield to like a moment that more than what you designed for, then you go to jail, okay? Because it's gonna fail and probably kill somebody.
All right.
Okay, did I answer you?
Thank you. Yeah.
Okay, perfect, guys. It's 1:51. We're going to break for 10 minutes. I will see you here at 2:02. Okay, 2:02.
I'm just wondering, is the other presentation